This is how we're getting the camera ready. That's the right chair. That's better. Yeah, that height is better. I think that's it. Yeah.
Yeah. Okay.
Yeah, that looks better.
It looks better.
If I scoot over here a little bit.
Yeah. If we invest in a and Pine's a little cut off, but it's
yeah, it's because of the lower thing, which I like the lower thing.
Yeah.
But if we hide the lower thing, you can see Pine a little more. There you go.
Yeah.
I think we should put the lower thing back on.
What are you doing?
I took away the banner.
Yeah. I like the lower.
All right. It's time for the live stream waiting video.
Okay.
This was just a sneak preview. We are actually live right now.
Yeah, okay.
Okay, hang on. Let me start the video.
Yeah.
Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Chris, can you hear this?
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello.
Hello. How are you all doing?
I hope the audio's okay.
Yes. Please let us know if the audio is okay.
As always.
As always.
We checked this before, but Chris said it was. What does foobar mean?
My understanding of
Oh,
foobar.
I can't say it. Is now that I'm seeing the letters,
Oh,
like
I've always
very
just-
badly up
yeah,
beyond all reason. That's what it says to me.
That's what it says to you.
So I'm trying to not get fired. So I think that's what it means.
Right.
I'm assuming that's what it means. I would like to say it, but I can't.
Yeah.
So,
Yeah.
yes.
Well, welcome everybody to another episode of Ask Us Anything About Electrochemistry. I'm Dr. Alex Peroff. This is Neil Spinner, Dr. Neil Spinner.
Yeah, thank you.
He didn't spend 5 years in graduate school to be called Mister. Just think about that, like Austin Powers.
Yeah. You know, the funny thing is that neither of us care that much about titles or whatever.
yeah,
And it's like any place, like, you go to the doctor's office, you go wherever, and they just say Mr. Peroff.
Yeah,
Like,
yeah,
whatever, it is what it is. And then sometimes it's like the only place I ever feel, and it's not like I'm upset either, because I'm really not that full of myself. I hope, maybe I am, I don't, whatever. But the only time is ever when people email with us, and it's like our email signature says like Alex
Yeah,
Peroff PhD. Like
yeah,
I couldn't help you if I didn't have this degree, because
right.
I'm further in my career than you. I'm not like better. I'm just older, right? Like that's it. And it's like, dear Mr. Peroff, Mr. Spinner. It's like,
Yeah.
Really, man?
Yeah, and you're a
Really?
graduate student, or
Come
you're an undergrad.
Do you call your professor like, Mr. whatever? It's like-
Yeah, yeah, or just have a first name basis.
I'm like, really?
No.
Do better than
We
that,
we
man.
will allow you. It is a privilege that you will be given.
Yeah, that's right.
So from now on, we shall be referred to as Doctor.
Doctor and doctor.
Yes.
We're gonna change the title of this to Doctor and Doctor. I'm derailing your intro. Please
No,
go on.
it's all good. So welcome everybody to another episode of Ask Us Anything About Electrochemistry. This is where Neil and I like to entertain any and all questions about electrochemistry, discussions about electrochemistry, because electrochemistry is a complicated subject, and we get lots of questions via email, YouTube comments, webinars, just even on the telephone when people call with a question. So this is a better venue, so to say, where you can ask it, and we can really take a deeper dive into some of the questions that you might be having with electrochemistry. So we are using, this is being streamed to YouTube, and we're using Restream as a platform to do so. We've noticed that maybe there's about a 20-second delay or so between what we say and what you hear, which means that there might be a time delay. So just keep that in mind as we go through the live stream. This live stream, we'll go as long as we can. We usually do this for about 2 hours, depending on how many questions that we get, and we aim to do this about every Friday, if possible. Last week I was out because I was traveling in Chicago. I was doing it for work. Also, for all of those who I met in Chicago who recognized me from either YouTube or live streams, thank you. It was very nice meeting you. This was it's called the CRC, like Inorganic Colloquium. So it's
CRIC?
Yeah, CRIC. Yes, Inorganic Colloquium, and it was very good as well. It was a good meeting. So, lastly, if you're watching this after the live stream, I'll try to put timestamps in the description that'll let you know when your question was sent, so you can just go directly to that question that is of the most interest to you. If we mispronounce any of your names because they're just names on YouTube, we apologize in advance for any of those.
I don't apologize.
I try to apologize,
Yeah.
especially if it's a Pokemon name.
Yeah,
Like,
I mean,
I should be getting that right.
I apologize to the Pokemon.
Yeah,
I suppose. Yeah, that's reasonable.
yeah. So, yeah. I think with that side, I think that covers all the bases of things. And so, if you do have a question, please type them in the chat, and we'll try to get to them as soon as possible.
And we can get to one because there was one question from Haifa Sauvé. It looked like just not too long ago. Typed in this question. Today, I would like to suggest to speak about. Sorry, it's a little small here. Yeah.
Oh yeah.
Not well resolved time constants in the low frequency domain on EIS spectra. And then the clarification was that not well resolved, I imply the signal, the points, they start to have the same minus Z imaginary and increasing Z real. And I think I know what you're talking about. I'll try to draw this for those who are not exactly sure what this discussion is for. So on the Nyquist plot, you have this phenomenon here. Basically, the spectrum becomes flat. Why does it happen? And what are the physical reasons for it? So I will try to answer this as best I can. To be honest, some of the answer I'm not 100% certain of. I have seen this phenomenon before. Am I sharing? Let's make sure.
Oh yeah.
Looks like I'm not sharing. Yeah,
Yeah,
thank you.
make
Okay,
that
perfect.
there.
Okay, so to the best of my understanding, or at least impression of your question. So if I have a Nyquist plot, I have Z real here, and I have minus Z imaginary here. And so let's just say a typical Nyquist plot, you might have something like that, right? So I have a semicircle, and then I have some sort of 45-degree line going off forever, like some Warburg diffusion. Sometimes odd cases in systems, I have seen what this question is describing, where you kind of get the, I'm just assuming you have a semicircle. You might not have a semicircle at all. I'm just assuming the first part of your spectrum. But basically over here where I'm starting is high frequency. So as I start to move to low frequency, you get something like this, where it just goes like horizontally. It's this odd behavior. And so this is what I believe is meant by the same minus ZI value, wherever it happens to be, but the ZR is right. It's changing. It's moving. And so the tricky thing about this, first of all, is that if you consider fundamentally a few things. So, okay, so a resistor, right? What does a resistor look like by itself? It's just a point. This is for ZR on a Nyquist plot. I'm just drawing what the most fundamental circuit elements look like. Okay, so if this is like 0, 0 is the origin. A resistor is just a point, and the value is the resistor. A capacitor on a Nyquist plot, and I'm just going to draw a different location just for clarity, but it's just a straight up and down line. Okay, and Alex's favorite inductor. If I can draw the loops, that's pretty good.
That's actually very good.
That is pretty good. I'm very impressed with
very
myself.
good.
Again, I'm just drawing these at a different position just for clarity. This could be here or here. Like I'm just drawing it for clarity so you can see the difference. But basically, an inductor is a vertical line that goes straight down into negative territory, basically. Okay, so almost everything else is an offshoot of these things. Okay, so what I mean by that is almost anything else, whether you have again, sometimes it's drawn like this. This is a CPE. Sometimes it's Q. So these are all the same thing. A CPE is just a variation of a capacitor. The closest that you can get is a CPE with a very small alpha, because if you have alpha of a CPE is 0.5, it'll be this horizontal line. So that's basically a Warburg. Okay, so this red line is alpha equals 1. And so as you decrease alpha, alpha equals here, like, I don't know, that's like off the screen here, like 0.2. So in some sense, you could say that a horizontal line is kind of like a CPE where alpha is really small, but it's still not actually horizontal. You see that it will still have an angle here. It'll still have some angle with respect to the x-axis. It's not exactly like a slope equals 0. So this is the tricky thing to me. So the first answer I have for you is that my impression when this occurs is that most likely it's not valid. Like the impedance data is not valid. So what you need to do, or what I encourage you to do on any data you have where this phenomenon is occurring, is to do Kramer's Kronig. Okay, and so if I had some sample, I might have some sample data somewhere on my computer, but I don't want to search here forever for you and, drag this thing down. But I have seen data like this before. I might have some, but basically, if you do Kramer's Kronig on it, sometimes what you find is that like the first part fits okay, but then this part will not fit, and you'll get like terrible. Like this will be the fit on your blue data, and it's bad, and it's like, well, it doesn't mean anything. Like it isn't a real phenomenon because it's actually just. Sometimes it's like you have drift, like your signal is drifting around. You'll get Lisa that looks like this or some crazy thing. And Kramer's Kronig can reveal that problem there for you. So maybe that's part of the problem is you have a diffusion limit, problem. Chris says, yeah, not steady diffusion limited at the near steady state. Yeah, so something about diffusion and steady state and not being a stable system, something like that is probably going on. And if the Kramer's Kronig isn't adhering well, that probably is what it means. If it does fit okay, honestly, I have very little advice to give you because I don't 100% understand why this has happened. I have seen this before, and sometimes I think people have had their own sort of methods of trying to interpret it. What does it mean exactly? Again, the best I could say is that possibly something like a CPE with a very small alpha could describe it partially. But even then, what does that mean? There's not a clear answer to that because a CPE with an alpha of very, very small is almost beyond a non-ideal capacitor or like non-ideal diffusion. It's almost like it's just a mathematical tool that fits data, but what does it actually mean? Like what's actually happening? That is really quite vague and almost entirely unclear. Ion concentration dropping up to, yeah, like any of these possibilities, right? If plating, ion concentration, diffusion, something about steady state, like those, anything like that might be the case. And almost all of those things, as Chris is giving some possibilities here, almost all of those explanations probably would fall under the category of like not real impedance. Like if something like that is happening, it's sort of fundamentally not stable or linear or whatever, right? Like over that time, and usually it happens at low frequency because it takes longer. So more time is passing. With more time passing, you have more possibility for like wonky stuff to happen, things to fall out of steady state, etc. So when that is your situation, not to say that finding an explanation of any of these possibilities is a bad idea, but probably continuing to try to fit the circuit of your impedance data is probably a bad idea. It probably won't get you anywhere.
Yeah. One thing I'm glad you mentioned is as we wait for more questions to come in, if they come in, it's always been interesting. And I know that last week I missed some discussion on inductive loops, my favorite subject. But to kind of Chris's points, it sounds like things like, okay, is the ion concentration dropping over time? Is something plating out? And I'm thinking, yeah, the system is no longer stable if those things are happening.
Right.
So it invalidates the EIS. But then thinking back to like these inductive loops, like, hey, if corrosion is happening at this thing, does that mean the system's no longer stable? Does that mean it's no longer valid EIS?
sometimes yes, actually. And this is one of these things that I'm not, it's almost like talking out of both sides of my mouth. So I do think that that is the case in some cases where there's this low frequency inductive loop.
Mhm,
It's like if it's corroding
mhm,
as I describe it before, which is, in short, it's like it's corroding more over time, which lowers the impedance because corrosion is a preferred electrochemical process. So it's
mhm.
corroding more, impedance is dropping, it curls, blah, 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 right? Where the
Yeah.
inductor is, I don't know,
Yeah.
keeps you
Oh,
up at
yeah,
night.
yeah, yeah, yeah.
But but effectively, because it's fundamentally changing, is that data even impedance anymore?
Yeah,
You know, I don't know the answer.
yeah,
My hunch tells me it actually kind of isn't.
yeah.
But the odd thing is that sometimes Kramer's Kronig will still fit it like okay. Like maybe there are
Mm,
times where that loop doesn't fit all that well, which is somewhat of an indication that it's not valid or whatever.
mhm.
But fundamentally, you can make that um loop, right? Like with ideal data, like with that 3-tiered loop thing, you could make
Yeah,
it and it fits Kramer's Kronig. So it's like, regardless of whether the phenomena makes any sense
yeah,
or
yeah.
not, which is a valid criticism, um, to throw you a bone here,
Yeah.
whether or not it makes sense phenomenologically, it still can work mathematically as a circuit.
Mhm,
So it's like my explanation is actually probably lacking from that perspective. And I don't know if I'm right or wrong. It's just my sort of intuition about what might be happening. But my
mhm.
my explanation is flawed from the perspective of what you said, which is that my explanation of it corroding or whatever, like fundamentally violates some of the probably the situation that the electrode is steady and stable and not changing.
Yeah.
It's like that
But
does
but that's not to say that you're not incorrect, because I think in some textbooks they do mention like a process is happening,
yeah.
which you would think would invalidate the EIS, but they still interpret and they still do
I mean,
some analysis
it
of it.
even calls into question. It's like, it's the trickiness or the danger of like, I don't know, doing impedance at a set point. Because
Mm,
you want to start like a lot of times you do it at open circuit potential because
yeah.
you're trying to get a background, but also, frankly, it's gonna behave better
Hmm.
because you don't have a lot of stuff going on. It's probably more stable
Yeah.
and your signal will be better, like in theory. So when you do it at a set point, you're running a Faradaic reaction. Now that doesn't mean it's not stable, but
Yeah. Yeah.
it does increase the possibility that something will be
Something is.
changing because you're
Yeah.
oxidizing or reducing something, and maybe that
Yeah.
reaction causes some, yeah, it's like,
Yeah. And it's a slower time scale. Like
yeah,
you could be oxidizing, reducing something, and it's stable, but it could slowly be like casting something on the surface. That could happen.
yeah,
But
yeah. But the last thing I'll say about this, and then
mhm,
I see that there's a question, we'll get
yeah.
to that, but is that the other tricky thing about this is that I said to do Kramer's Kronig is that one of um, the things you have to be careful about with Kramer's Kronig is that it is not likely to give you a false negative. In other words, if Kramer's
Right.
Kronig doesn't fit well,
Mhm.
it almost certainly means your data is poor, in at least in the frequencies where it
Yeah.
doesn't fit well. But if Kramer's Kronig does fit well, it probably means it's okay, but it's more possible that Kramer's Kronig gives a false positive than a false negative.
Yeah.
So like in this case, it could give you sort of like, oh, well, this loop is mostly okay, but maybe it's not for other reasons.
Yeah.
So Kramer's Kronig is a little tricky. I like to suggest it often, but it's better to suggest it as a way that's like, if it's bad, good, you've got some good information. If
Yeah.
it's good, okay, proceed with
Okay.
caution.
Yeah.
Probably it's
Yeah.
okay, but it's not 100% that your stuff is okay because it's a
Mhm.
mathematical transform and it could be giving a false positive.
Yeah. Yeah. That's true. Okay. So we have a question from the audience from Pepetto. Hope I'm pronouncing that right. Pepetto. What is your opinion about non-faradaic biosensors? Any concerns regarding performance compared to faradaic biosensors? Um, Well, I haven't heard of non-faradaic biosensors, but my guess about what they are, and Pepetto, please correct me if I'm wrong, is normal biosensors will work based off of a Faradaic reaction. So somebody has their sensor, which maybe has some kind of carbon screen printed on some electrode, maybe a piece of paper or something like that, and then they put maybe an enzyme, some kind of whatever the sensing thing is, and then a Faradaic reaction is required between the analyte that you're trying to measure, what you're trying to sense, and the surface. So an electron transfer has to occur to give you a signal, and that would be a Faradaic biosensor. A non-Faradaic biosensor would be something along the lines of, if that object is in the vicinity, it's not causing an electron transfer between the surface and your analyte, but the analyte is changing something. So maybe the electrical double layer, for example, or it has some kind of non-Faradaic, a non-Faradaic thing is happening that's unique to that analyte, which it allows you to sense it. So I have a lot of thoughts and opinions if that's true, if that's what it is.
Yeah, my impression would be that a Faradaic biosensor would be stronger, um, simply because non-Faradaic processes like capacitive effects
Mhm.
are going to be present like all the time, no matter what.
Yeah.
So if you're having a biosensor that's trying to detect the capacitive impact of one specific species compared to the background or something of that nature, how do you know? How do you clarify that, right? Like the benefit of a Faradaic process is it has a particular reaction speed and it has a particular like E0 that it occurs at, right? And so it's
Yeah.
like you can not also easily all the time tell where deconvolute everything, but with a Faradaic process, you know that you're at some potential, something will be driven.
Looks like we're getting a little bit of
Yeah, some
clarification a bit
clarification.
more. Let's put this up. You don't need the redox solution when measuring with non-Faradaic biosensors. You can measure directly in the sample. I just wonder if they perform worse than measuring in Faradaic mode.
My impression is it would be, but I could certainly be proven wrong if I saw some data on it. I'm also not familiar with the difference between the two, but it's just my impression is that a non-Faradaic sensor would be more fraught for error because it depends on a lot of things. Like,
Mhm.
what are you trying to sense?
Yeah.
Like, if you're trying to sense some salt, and you can correlate, let's say, the like capacitance with the salt concentration or something,
Mhm.
like, okay, maybe you can do that, right?
Yeah.
And so you're gonna I don't know, correlate capacity, but it's like your how much background salt is in your sample. Like,
Yeah.
are you taking your sample from a lake or a river or the ocean or a biological sample? It's a biosensor, right? So,
Mhm.
like, is it blood? Is it
Yeah.
is it some sort of um, serum? Like, right? There's a lot of like options for what the sample comes from, and if there's any variability in the salt content, for example, in your sample,
Mhm.
it'll affect the non-Faradaic response,
Yeah.
right? And
Yeah.
so the point of this is that if, like, let's say all of your samples have the same background salt concentration or something,
Mhm.
but the only thing varying is your analyte or your whatever you're trying to study. Okay, well
Yeah.
then probably you could subtract background and correlate or something like that.
Mhm.
But it seems like it would be difficult, especially if you're getting like
Yeah.
real world samples, to control for that.
Yeah.
And so my impression, without more information, I suppose, is that I would anticipate that a Faradaic sensor would be a stronger sensor.
Yeah.
That's my
Yeah.
impression.
Yeah. I think I agree. I think when you have a Faradaic process, you have a whole lot more selectivity, which is something that you don't always get, perhaps in a non-Faradaic
Yeah, the
system. I mean,
selectivity is a big one.
but another thing that might be interesting to keep in mind. I actually, when I was I was a postdoc for a little bit, some people in my research group they were using Raman spectroscopy to actually they were using Raman spectroscopy along with, not necessarily, they weren't doing machine learning at the time, but they were basically able to collect a tremendous amount of Raman spectra for like blood samples or something like that. And without understanding the science, they were able to use mathematical models, computer things, and correlations to say, like, oh, if we, we looked at 100 or 200 or thousands of different blood samples that we knew were of a specific type, and we could maybe say, all right, if we had an unknown blood sample, we could say, based on our modeling, like it's A or B, or A or B is present in it. And it was just based on the mathematical modeling. It actually, like, no one really knew why you got A or B, but it was just statistically there was something found in that signal that the computer found
Yeah.
that it could identify as, oh yeah, this A or B is in it, and
It's
we
like
think
pure
it's
empiricism.
pure
basically.
empiricism.
Yeah. Which is reasonable
Yeah,
and powerful
yeah.
in many cases, I think. But yeah, the trouble is when you're trying to like correlate that with like theory or phenomenon of what's
Oh, yeah.
happening, it's not always
What's actually
obvious.
happening.
Right. Yeah, exactly. So it depends what your goal is, right?
Yeah.
I mean, a lot of times, I guess, for a sensor, if you, to that point, if you can make a sensor where you can use empirical relationships, no, that's probably fine, right? I
Mhm.
mean, so maybe
Yeah.
it's possible in that way.
Yeah.
But it depends. Like if you're looking at it from a more academic perspective, and you need to like understand the theory of what's happening, and
Yeah.
it'd be more difficult.
Great for engineering, but
Yeah.
chemistry, what's actually happening? Oh,
Yeah.
much harder.
Engineering's better than chemistry anyway. It's fine.
That's true. All right. So we have, and of course, Pepetto, please add more if you want us to talk more about it. But they're 2 PhDs, 3 if you include Chris. So you're gonna have a lot of opinions.
That's right.
So we have a question from Bahar. I have a 2 electrode system with a silver chloride as the reference electrode / counter electrode that I made out of silver wire. Now I need to change that to platinum wire due to biocompatibility issues. I don't see a sensing peak in my CV anymore. And he continues to say, I can't change the potential range anymore as the OER process might start. What is your opinion on that? Well,
You've got a pseudo reference. That's what's happening.
yeah. So definitely, so even when you have when you just have silver in your system, you've just silver by itself is a pseudo reference electrode. Its potential is going to shift as a function of the system that you're in, whatever it senses. And platinum similarly could shift the potential for this 2 electrode system. But if you have, and I guess I can share my screen very simply. I think about this from think of this mostly from just like a CV perspective. Everybody see everyone can see
Yeah.
my screen. So I'm going to think about this from kind of a cyclic voltammetry perspective. It just gives us a place to look at. You have voltage, you have current. And this is voltage versus silver. Like silver, maybe silver plus, maybe silver whatever. You're going to have some kind of response, and maybe I'll make this response in red. And let's say, and you said that there's a sensing peak, so maybe there's a sensing peak that's something like this. Let's just do that for now. We can make it like this. But then you may switch to versus platinum, and then all of a sudden, like you're all the way, like this same sensing peak is like all the way over here, right? It goes out. Have this little weird feature. So now these peaks have shifted by some value. So that's one big thing. You're dealing with the difference between platinum and silver. Um, but then these are also not stable because the reference electrode potential is a function of the reaction, the Nernst equation reaction, whatever's the fastest one, and with sufficient concentration near the platinum and near the silver electrode. So these are going to drift around, they're going to shift, and especially in the two electrode system, they're going to shift a lot because any current that you apply or any charge that builds up on the working electrode is also going to have an opposite charge on the counter electrode, counter reference electrode. So definitely these things are going to shift around, but your OER should also shift also. So maybe the use of platinum, because it's also the counter electrode, does decrease your potential window in a way, but yeah, I would say the OER should shift as well. Like however much this is shifting, the other, your OER is also shifting. So if OER happened in this region, it might happen in this region or this region. It depends. So hopefully that kind of explains, like, okay, if the potential shifted a lot and you can't see it, it's like, well, you need to adjust your range, and maybe you do have to go to something much wider that's in the OER. But what's strange is that the peak should still show up, because if you're using a potentiostat in a two electrode system, the current you measure is at the working electrode. So there shouldn't be any reactions on platinum or silver that you're seeing on the working that's like contributing to that signal. So I hope that kind of helps. Let's see. There's a little bit more information.
Yeah, he says that the silver wires were chloridized. So it's actually he's using silver chloride. So I would actually just add in that it is, even in the situation before you trying to change to platinum, you're using AgCl as your reference and counter. Everything Alex just talked about is still possibly the case. So you're seeing a peak and everything, but one of the problems, in addition to the fact that the peaks are going to shift based on what your reference or counter is that it's not necessarily even stable, because as you're using a two electrode system, the potential or the voltage at your counter reference side is exactly equal and opposite. And so it is going to be the sensing part and the auxiliary electrode. It's going to have the opposite current, whatever, flowing to it. It's going to have the opposite potential. And whatever the Nernst equation dictates that potential to be is where its set point will be. And that will change. So like the silver chloride couple, and perhaps you're getting lucky in some sense with the first test that you did, that you're doing a CV. So like if you're going plus or minus 1 volt and whatever your range is, like that means that you're actually applying plus or minus 1 volt or whatever on the AgCl. And it's like, this is not advisable in general. Like with a 3 electrode system, there's no, really almost no current or flow at all on the reference electrodes. It's only used to sense, right? And so that like 200 whatever millivolt potential that is dictated by the AgCl is like set, it's firm. But if you start running a potential and a current through your AgCl, kind of all bets are off, right? So my first, well, you said it's a biocompatibility issue. So my first, just general point is that, are you not able to use a 3 electrode setup at all? Because it's just not easy to get stable. I mean, it's not always easy to get a stable situation with a 3 electrode when you have a pseudo reference, but make it worse with a 2 electrode. Because at least with a 3 electrode setup, the reference can drift because it's not a stable couple, but at least it's not drifting because you have current going through it that's affecting its surface reaction actively as you shift. So part of it is like what Alex said, like maybe if you're worried that you're going to start doing OER, well, maybe that's not the case, because it's like the potential for OER is also going to move Like it's not, you know what I
Yeah.
mean? Like everything moves. Like if everything's moved more positively or something like that, right? Then your peak that you're looking for is shifting, as well as OER, as well as HER. Like everything shifts. The whole potential window shifts.
Yeah.
But also it's like as you start applying a higher voltage or a lower voltage, whatever, you're changing the reference set point actively. So that clouds up things very badly from the perspective that like you might have, like if your reference is here and you're scanning positively, you would want to be like from like 500 millivolts to 1 volt and back and forth. But if this thing is moving with you, it's like you're not actually scanning at all. Like they might be moving in opposite directions. They might be like, you don't know what the reference is doing. It could be all over the place. You know, that's the point, right? Whether it's a platinum wire or it's the AgCl, because you're doing a 2-electrode system. There's current and voltage effects that are changing the Nernstian equilibrium, whatever, at that counter reference all the time, regardless of what it is. So you have to be aware of that you are going to have a hard time getting stable situation. And maybe if you do, you're fortunate for whatever you're trying to test. 3-electrode, not an option, unfortunately. Yeah. So you check the EIS on the AgCl and it doesn't change. Yeah. So you might be fortunate that when you're using the AgCl, that this sweep, these potentials you're using are not changing maybe dramatically the AgCl couple of potential, but it could. That's my point, is like, you know, for example, you said that you chloridized the Ag wire in KCl, right? That's a way to make the AgCl, right? You what, reduce it or something, or oxidize? I was missing.
What the
Like you
AgCl?
oxidize Ag in KCl and you get AgCl.
Oh,
right?
Yeah. So the redox, reaction for the silver chloride reference electrode, depending on how you write it, but it's silver chloride solid plus electron gives you silver solid plus chloride ion. And
Right.
that makes it easier to calculate because based on the equilibrium, the potential's just based on the chloride ion concentration. You don't have to worry about like silver plus concentration in that case.
But it's like what you might be doing, and you say that you check it and it doesn't change, and that's good, but it actually might be changing to some degree. And because you might be driving that exact reaction, like that reaction has a potential that you care about or whatever. But by sweeping and using it as the counter electrode, you're applying a positive or a negative current to the AgCl, which could be resulting in the removal of some of the AgCl or its reduction or whatever, you know? So that could be bad.
One of the things you can, I think there are I have a couple ideas of stuff you can try to help you with this. One is that you said that you're not seeing the sensing peak. Could you, as a separate experiment, add other redox couples that you know about, say ferrocene, ferrocyanide, ruthenium hexamine? I'm just naming a couple things.
Yeah.
But like add it to your system and see where they show up. Like these are well documented.
Yeah. That's called an internal standard.
Yeah, an internal standard. Add an internal standard and see if it shows up in your silver chloride.
And then with your platinum.
And then also with your platinum. See if that happens, because that would also indicate there may be some other sensing potential that's a little odd or something's off when you move to platinum.
You could also try a different material too, because platinum is a nice noble metal and probably works well with a lot of systems. You could try something like stainless steel, hastelloy, something like that might work okay, because those are also pretty what's called non-polarizable, which means their potential doesn't change too much with it addition of with some current effectively. So you might actually just have different levels of success if you try different metals for your counter reference. As you said, especially if 3-electrode is not an option. So try some, some other metals. If you can. I mean, to be honest, it might be easier. Like stainless steel is probably cheaper than platinum. So it might be a little easier to obtain some 304, or I don't know, 303, 313, 314, whatever. Some stainless steel, get a rod or a stick of stainless steel, try it. You might have some success there, I guess.
Another thing I would recommend you do during your experiments is to measure the OCP multiple times. Like,
See if it's drifting.
yeah,
like, a
see if it's
lot.
drifting. Measure it before the experiment, measure it after the experiment. What kind of changes are you observing? That'll also give you a little bit more information.
Yeah,
about
and
the
if
system.
you measure it with either case or both cases, and it's
Yeah.
like it's just moving in a constant straight line down or up, it's probably an indication of some of what we've talked about, which is just not stable,
Mhm.
right? And it's like it would be hard, and this is why that internal standard can be helpful,
Yeah.
because you'll scan back and forth, and that hex or ferrocene, whatever peak that's your internal standard, will show up like at a different potential every single time you scan.
Yeah.
And
Yeah.
it's like, it doesn't mean you can't do anything, but it does mean that you're gonna have a harder time finding peaks and figuring out what's where and everything.
Yeah.
And what potential to use, because it's moving all the time. This is the tricky thing about using a pseudo, as I said, this is a tricky thing about using a pseudo reference. And the trickier thing is that not being able to use 3 electrode.
Mhm.
Maybe in the future you'd be able to get a potentiostat, right? That has a sense line. You can use a 3 electrode system, because while not perfect and still drift can happen, you would probably reduce some of that if you could have a reference electrode, like a 3 electrode setup,
Yeah. That's correct. So hopefully that's helpful. Bahar, please let us know if you have any further questions, clarifications, things like that. Chris actually mentioned something very, very important, which is if the electrolyte system isn't chloride based, perhaps verifying that you're not getting significant silver ions in solution eroding off your electrode. And considering that Bahar is working in it's like a biosensing, one thing I studied a little bit or did some research on was that silver ions have antibacterial properties. So yeah, maybe silver chloride isn't good for your system, because silver ions that leach out could be killing your system, or your biosystem by chance.
Antibacterial is not always a good thing, apparently.
Yeah,
Not
yeah.
if it's part of your sensing. Chris
Yeah.
also says that one of the things in the real world is that ideal cases, they don't exist in any appreciable extent. This is true
Yeah.
unless you do engineering, because in engineering, at the very least, in many of my classes, for example, the treatment goes like, take the ideal thing and then realize that it doesn't ever happen,
Yeah.
and add some exponent, and then it works. It's like you just add some factor. It's like the joke we always had in undergrad was you use it was one of my friends named it after himself or whatever. It was like this factor or whatever, and it's defined as the correct answer over your answer. So you do the math out, you use the fundamental equations, and you get 10, but the answer is supposed to be 15. Well, then the fixed factor is 15 over 10. It's the correct answer over you. So every
Yeah.
test you do, you just multiply what you get by the correct factor,
by the correct,
and it's the correct answer. It works. I don't know how it does it. It works every
yeah,
time.
yeah.
That's a little magic trick for you. So
Yeah, that's
yeah.
that's almost
It's cheating.
exactly what activity is like.
Yeah, that's
chemical
exactly. Yeah.
It's just like concentration is equal to like a gamma activity coefficient times the activity, and that gives you the concentration.
Yeah,
It's
it's just made up
or something like
It's
that.
literally because all of the theory in the world about concentration and ionic strength and all this stuff, or whatever, when we do real measurements, we're like, oh, well, that is what it should be. That's not what it is.
Yeah.
Well, it's like 80%. All right, times 0.8.
Yeah.
Okay, it works.
Oh, and then Chris mentions, and then you realize that engineers have no idea how the real world actually works. Just ask the guys that designed bolt heads that are impossible to access to tighten. Yes.
Yeah, I think the reality of everything is that almost nobody really knows anything.
Are these bolt heads on I guess you got a new house from, I know you're dealing with an escrow problem a couple weeks ago. So I think we've both had to deal with a lot of just house issues.
Yeah.
ball
If they're
pens.
impossible to access, like how do they even do it in the first place? Like
That's a
they
great
tighten
question.
stuff and they build some manifold over it and you can't get to it. It's like this was smart design.
Yeah.
it's-
Well, I mean, I think there's a lot of stuff in general. Like sometimes just an item has like these caps over it that protect the screws on like an electronic or something, and it's like you have to pry them off with a screwdriver. But like people do everything they can, or companies do, to like kind of hide where the screws are or hide how to access certain things.
Yeah, like I understand like aesthetically, maybe it looks ugly, so you don't want to like I don't know, like it's an eyesore or whatever. But also like, yeah, but I need to like fix it sometimes. So
You're gonna have a conversation with Tim because
yeah,
Tim's like you can't sell ugly things.
it's true.
Everything needs to be pretty.
Well, I am the engineering type, and so when it comes to like what form versus function, I'm almost always on the function side,
Oh yeah.
which is why I'm grateful for my colleagues like you and Tim who understand that form matters. Not that I don't know it matters. It's just that I'm more like, oh, cool, it works. This is great.
Yeah.
And then later on, Tim's like, what did you do? I'm like, I don't know. It works. Who cares? It's like nobody's gonna buy that. It's ugly.
Yeah.
It's true.
Let's see, just saying, Papetta's just saying thanks for the discussion on non-faradaic.
Yeah, hopefully that was useful. We
Awesome.
do often get these questions about stuff that we're not entirely familiar with from like the specifics. You know what I mean? Like we've never actually tested this, but hopefully our understanding of the processes was somewhat useful for you.
Yeah. Yeah, and then Chris just mentioned that what actually happens is the guy actually has to build and figure out how to make it something that functions despite the engineering.
Despite the engineering, I feel like it functions because of the engineering. Wouldn't you say? I don't know if I can sit here and listen to you smear engineers all day.
I am curious, Chris, a little bit. Like I feel like you've been on the live stream, or commented a lot on the live stream, and it's like we learn little bits and pieces about you. Earlier you were mentioning about leaving academia or something along those lines.
It's a good decision.
And so yes, we support that.
Yes.
So we're always interested to learn a little bit more about the people. We've gotten a lot of interesting like emails, comments, follow-up questions from regular viewers, and so it's always nice to you're a real person on the other side.
Yeah, you could get your camera and join us too if you wanted to someday.
Yes.
I don't know, maybe you mentioned it before. I'm not sure if you can or can't or something, but you could join us live and chat and just answer the questions for us while we sit here and look pretty.
Yeah,
that's
right.
fun.
We'll find like a Pine Research T-shirt. Like we got plenty.
Yeah, we could send you an extra, polo shirt or something like that. You
that's
could
right.
Be an honorary member of our team.
Yeah, that's right. Also, for those who are wondering, there's a bunch of boxes behind me.
Yeah.
They are full of potentiostats because Neil and I are going to be doing an electrochemistry workshop later in November. So just to keep that in mind, we do these live streams, but we also do in-person electrochemical workshops. So if that is also something that you're interested in, we're happy to do workshops for you in a way, and but also we haven't actually figured out a good way. Like if you follow us on social media, like YouTube and Twitter and even LinkedIn, we do post about upcoming workshops and webinars and all kinds of stuff like that can happen. So you can learn a little bit more about them or even take part in them in the future. So
yeah,
that's happening.
We've done those a handful of times in the past. I think we're going to try to do more of those in the future. It just depends on where and which, like, universities and those kinds of things we can reach out. But doing those things in person is pretty fun, I think, because you get to really like meet with people and click the buttons yourself and touch the instruments and set up an experiment yourself. Those kinds of skills are useful, right? More so than, I shouldn't say more so than what we're doing right now, but in addition to the live stream kind of stuff, I guess. But
there is real knowledge in actually doing the thing yourself. Um, so yeah, there's knowledge that can't be acquired just through the live stream. There's like in person, touching the cell, putting it together, all that kind of stuff. So absolutely.
It looks like Haifa is here with
Yes.
questions about or it looks like you're following up. We'll give it a second here, but that was the question originally about the low frequency flat lining kind of thing. So
Yeah.
I'll let you sort of fill in if you have some more comments about that or some questions or anything like that.
Yeah. And if you
But,
just joined, I guess it's and let's see.
I see it during oxygen evolution.
Oxygen evolution.
Yeah.
Oh.
It's perhaps more reason to believe that there is some unstable situation happening. One of the fundamentally tricky things about doing OER and HER is that you're generating gas. And so when you're doing that, you're sort of fundamentally breaking up the electrode electrolyte interface in liquid phase. And it can lead to some strange stuff. I don't know exactly how that translates to this sort of flat system that you described in your question. It's a bit strange. I still defer to sort of my explanation, which was about Kramer's Kronig, seeing if it's a real stable phenomenon, or you maybe reveal that there's some instability at those frequencies, for example.
Is it possible, like, if this is happening during the oxygen evolution reaction, does that mean, like, well, you're doing EIS at specific potentials, right? So
Yeah.
you could, in principle, maybe like do EIS at a potential below where you're seeing oxygen evolution, and then like near it, and maybe would that actually change the EIS, the low frequency EIS region? That's what I'm curious about. It's looking for changes in the EIS spectrum, I presume. But
Yeah, I mean, it's hard to gauge exactly, of course, without seeing the data and things like that. Yeah.
Oh, sorry, I just I blocked him.
Yeah, it's a bit goofy. It's fine.
Yeah.
We appreciate
Take
the
care of trolls.
lightheartedness, I guess.
Yeah. Okay. Any ionic species that may be let's see. Oh, I was just gonna any ionic species that may be getting depleted, plating oxide formation on the electrode. And then actually Haifa's mentioning that
It forms
it
oxides.
forms oxides at the surface.
Yeah, it's going to with the high. You must be at a
Yeah.
high potential, so you're going to be having something like that happening.
Yeah.
I mean, the tricky thing here, of course, is twofold. Like, so if you're doing Kramer's Kronig validation, and you're finding, again, it could be a false positive, but let's just say, for argument's sake, that your data does appear to be valid. You sort of have twofold problems here. One is you can sort of describe the processes with any of these possible explanations, like maybe in your paper, in your summary, or something like that. You describe it as, well, there's some plating process, or there's surface oxides. Like, maybe those are some of the explanations. But what it doesn't help you do is fit it. It's like analyze it, because again, it's like I showed, there isn't really any good circuit analog that does that. Like, there isn't really any, other than CPEs with really low alphas, or like a Randall's element with a CPE with a really low alpha makes like a really flattened semicircle, but that's still a semicircle. It's not like a flat line, right? It would still have a semicircle behavior to it. You don't see that in the literature. Yeah, honestly, you probably don't see it in the literature, because when this happens, people are probably not publishing the data because it's not it might not be valid, or it might be it could be other stuff. It could be like a weird hardware thing. Like, it's hard to know. I'm not really convinced it's a real phenomenon. I do
Yeah.
think it's possible, especially maybe if, you have some Kramer's Kronig that's saying it's valid. I'm not going to say it's 100% like definitely not a valid phenomenon, but I do think it's tricky because with almost every valid phenomenon, even if the circuit's rather complicated, there's still in theory a feasible way to fit it and
Yeah.
analyze it, and this one kind of lacks that.
This is I'm kind of going on a loop, and Haifa, please correct me if I'm wrong. Is it possible, because I know sometimes what we'll do is, if for some reason the instrument is unable to make a measurement, we'll actually just put like a 0 point on on the data stream. So is it possible that once you get to this low frequency region, can you validate that, like, I actually do have those data points are actually showing up as being real, and it's not like the instrument saying, oh, I had a hard time measuring at the low frequency? Because that might happen. Right.
Yeah.
If it's drifting all over the place, the instrument may say, I don't know what this data point is. I'm going to put like 0, but I kind of know that I'm going to keep going to the right. And I just get zeros in a line that looks like I have a low frequency increase in the real impedance. But it's actually like an
Yeah.
instrument artifact.
Yeah.
We haven't seen the data, so we don't know.
Making sure that the software is not sort of providing you a dummy point.
Yeah.
That is a good point. I'm guessing that's not the problem. You
Yeah.
probably are familiar with your software and potentiostat,
Yeah.
but that is a good point to make, just to make sure, I suppose.
Because maybe it is on like a slight angle. And
Yeah,
in that case, your
if
CPE.
if it's at a slight angle, yeah, exactly. But I have seen this phenomena where it does go horizontally. I have seen, maybe not published, but I have seen it like in a customer's lab, or I've seen it. Customers have sent me this data before. Like, I've seen it. It's not often. It's pretty rare, but like, I have seen that happen before, and it really has been a similar thing in the past where it's like, oh well, this is not valid. Like it was a drift, some sort of drifting at low frequency because of diffusion or something caused like the OC, like with the situation we talked about with the 2 electrode earlier, like the OCP is drifting, or something crazy like that. So it's like, actually your applied set point is not stable over however many minutes that's going on, something like that.
Yeah.
Right. And so it's actually just not stable. So it's a bit of a bizarre phenomenon, but I'm not convinced that it's a real phenomenon. Try to do the spectrum from low frequency to high. I suspect that won't help. You can try. Generally speaking, you don't want to go from low to high. That can cause other problems. You might just now propagate any sort of drift or issues throughout the whole spectrum instead of just at the low frequency, because you're starting where it's already drifting. Whereas when you start fast and go to slow, presumably the fast frequencies are not enough to disrupt any sort of equilibrium. And then the other part is that fundamentally, at least for most potentiostats, yeah, everything's good. These are phenomena are reproducible.
All right. Yeah, just checking.
That's good to know. Yeah, just as a case there. Yeah. But fundamentally, a potentiostat usually performs better and sets its automatic progression more easily when it goes from fast to slow. The way the filters and the gains and all these kinds of settings work, a potentiostat will perform more ideally going from fast to slow. You can certainly try low to fast, low to high. I don't anticipate it would improve your results. That's just my guess, but you can certainly try it.
Could you also, because I mean, remember in EIS, like, it is the spectrum, but like each data point is like you're just, it's like, it's just collecting. And like that data point in some cases should be somewhat steady state. So maybe you could find out, oh, if I just did this frequency just over and over again, getting a really good value at that point.
Like if it's starting at 1 hertz to 100 millihertz or whatever, and it's like moving along, and then exactly. If you just do 1 hertz over and over and over again, if it's also moving, that's probably a drift.
Yeah.
Of some kind, right? So just do 100 millihertz point 50 times in a row or something, does it stay relatively constant with some error, or is it moving as well? Because then it's like, well, the changing of the frequency isn't doing anything. It's actually just the drift at low frequency at slow speeds or whatever. The other thing that I was gonna say, what was it? Lisa's, you are fine. You check it out. Yeah, you have a stabilization step before. So yeah, so I was gonna say, so you say the Lisa's you are fine. So yeah, you're able to look at the Lisa's you. That's the other thing I was gonna say. If you look at the Lisa's you, do you see any sort of disturbance with them? I mean, everything you keep providing for more information is more evidence, perhaps, that it seems like it's a reproducible and actually expected phenomenon. Which again just makes it really harder, because if it is a real phenomenon, I don't exactly know what the right form of analysis is. It feels like a diffusional kind of similar, like it's an offshoot of diffusion, because diffusion is usually a line at some angle, and it's like this is like an extreme flat line, so it's like some sort of diffusion, but I don't totally understand.
There's a part of me that's like, we kind of would need to see the data.
Yeah, part of it would need to, yeah. Out of stability
Yeah.
due to bubbles. Well, see, that's tricky though, because you say it's out of stability due to bubbles. That's a possibility. But if your Lisa's you look fine, those two things are not necessarily coherent together.
Yeah.
Because if there were bubbles, I would expect the Lisa's you to look rather disrupted. So I guess it's curious to me, like if you have bubbles, in other words, if your Lisa's you look okay, like nice and smooth ellipses or something, right?
Mm-hmm.
I would not expect you to have bubbles, because bubbles would probably disrupt the Lisa's you. Yeah. So anyway, good luck. Hopefully this, maybe it's just nice to kind of air some of the problems out loud for us to talk through it. It's kind of interesting. I mean, this is a phenomenon that it also eludes me, to be honest. So it's nice to talk about it, kind of think about it, think it through, get Chris's comments are helpful as well.
Yeah.
Please go ahead and follow up with us if you want. If you learn anything, I'm always interested in hearing back about some of these problems that we talk about on these venues, because sometimes it's just as educational for me as it is for you.
Yeah.
Actually, a lot of times it is, because we're learning, about these phenomena through all of you as you're asking your questions, which is really kind of neat.
Yeah.
That's our email address.
Yeah, that's our email address.
If you want to send some data, or just send any email to us to sort of like, hey, this is what I found or something, we'd be happy to continue discussion.
And tier 1 members can join us on Restream, and you can show us your data.
Yeah,
we
you can share your screen.
Share screen, and that's another option, right? So tier 1, tier 2 members have the option to just kind of talk with us, not just through chatting, but actually share data. So we can do that too.
If there is a porous structure, the bubbles are forming a stable layer, that would be tricky. That would mean there's some uniformity of the bubbles, which is possible. I guess it would depend on the microstructure of the electrode, and if you're able to visualize that with some microscopy, like Chris put earlier, it would be interesting to see. But I guess the other part of this is if you do have a porous structure, you could consider a transmission line type. Now, again, it doesn't exactly explain that horizontal line. A transmission line usually is slightly different, but if you have a porous microstructure, it does suggest that a transmission line could be an appropriate method of analysis as well. So you could consider something like that if you're not familiar with transmission lines. You could look into that as well.
Yeah.
And again, it passes the KK test. So that's good. But again, it is possible to have a false positive. It's possible, right? So just be wary. It is not a guarantee that your data is stable just because it passes. Unfortunately, it's like, it's not a good news, right? It might mathematically somehow work out, but there's still really no good circuit that will fit it. You know, because what Kramer's Kronig might actually be doing is fitting like an infinite number of Randall's elements. It's
Yeah.
like you can imagine that one method of fitting a horizontal line would be like an infinite number of semicircles all looped together, right? Like
Mhm.
if you imagine like two semicircles together, right? There's two humps, but if I put 3, the amount of curvature decreases. And if I put 4, the amount of curvature decreases. And 5, like eventually you have so many
Oh.
semicircles that there's almost no curvature and it would just be like a straight line. But like, does that
Hmm.
suggest that your actual system involves
Yeah.
7,000 time constants and a bunch of Randalls? Like it doesn't
Right,
make any
right.
sense.
Yeah.
So that might be a situation described about why Kramer's Kronig will fit it, because it's fitting like a ton of Randall's elements to just make this pseudo horizontal line, but it's actually just a bunch of Randall's elements. It doesn't make any physical sense.
Yeah.
So it's tricky. Yeah. Yeah. Try low frequency and keep us informed.
Yeah.
Yeah. Poor structure manifests 45 degree at high frequency. And you have this example. Yeah. Yeah, exactly. The high frequency. It doesn't answer the low frequency kind of a thing, but yeah, exactly. The transmission line, poor microstructure usually has that diffusional 45 degree behavior at the higher frequency instead of the lower frequency. So that does at least answer that part of it, which is that you might have this porous microstructure, at least can guide some of your thinking along
Yeah.
what's going on. Yeah.
Looks
Looks like we have another question about nickel.
Yeah. So Pratesh is asking how to coat nickel sheet on both sides. And so I'm assuming, Pratesh, you're talking about electrochemical coatings. But generally speaking, assuming that you have a flat nickel sheet, be a nickel foil or something like that, you probably want to take an edge, clip onto it with like an alligator clip or something like that. And when you put it into an electrochemical solution, so I can just maybe visualizing it is a little bit better. So let me erase this, but I can at least show you visually what I'm talking about or thinking about. But if you just have some container, all right, some container, I've got my special electrolyte solution, and I think it's going to be green because you're coating copper, I don't know, something onto your nickel. So you have some solution, you have
Definitely green.
green plating solution,
There's so many green solutions out there.
and there are these things. I'm just going to draw this up to the side, and we can show later. But there's like, we sell these types of electrodes or holders that have an alligator clip on it. So it just has kind of these teeth on it. And this isn't the best picture, but those are supposed to be teeth. And then you can have your sheet of nickel, and then you can place it into this solution. Now you're gonna have to have you'll need a reference, probably. Yeah, you may even be able to do this with just a 2 electrode system. But you'll have a reference, some water. This goes out. And then you're probably going to either have a platinum or a graphite rod counter electrode, maybe graphite rod, so that you have a larger surface area. So that's a big rod of graphite, and that's also colored. So you would have this kind of 3 electrode system. Maybe you have this in some isolation tube to prevent whatever's generated at the counter electrode from interacting with the solution. But this allows all areas, this configuration allows all areas of the nickel sheet to be coated when you do some kind of coating experiment, perhaps electrochemical coating. So that's kind of what I'm envisioning per sheet. So hopefully let me know if that makes sense. And if we can do is can show you a picture of kind of, it's a product that we offer, but at the same time it might at least give you a visualization of what I'm proposing. So I will let me just make sure. Okay, so this is for, oh wait, no, that's a separate thing.
Yeah.
Separate question. Oh, where's my
Are you sharing more about this?
I
or-
was gonna just share a picture.
I see.
But
I was getting something to talk about. Chris's question is asking about transmission line.
Oh, okay.
You can show that.
Yeah.
I have a paper.
So hopefully I'm showing this. This is does it show up?
Let me check.
the-
Yes.
Yeah.
Yes.
So this is just it's just a kind of a stainless steel rod. There's a little alligator clip at the end. This is just a product that we offer. You plug your working electrode in, you clip your nickel foil there, and then yeah, you're able to just start, and we have these in various lengths, things like that, whatever your system is. So that is what I would recommend for your system, Pritesh. So hopefully that was helpful. And then you said you had something for
Yeah, I mean, Chris was just asking how analogous to the transmission line theory of electronics is the electrochemical concept of a transmission line. Is termination modeled the same in that case? So I'm not like very perfectly well knowledgeable about the actual electrical theory of like the electronics of a transmission line. What I'll say is a couple of things. So my understanding, and you might actually sort of have more knowledge about this than I do, Chris. So correct me if I'm wrong, but essentially the transmission line comes from poles. These are supposed to be pole like with electrical poles, right? I'm terrible at art, but so it's like these are electrical poles, and you have the wires going from pole to pole, right? Whatever, like along the side of a road. So you have the electrical stuff and you have your wires. And effectively, this is a transmission line, is that you have resistance through the ground, you have resistance through the pole. I know they're not all resistors, so pardon the just ridiculous oversimplification here. But essentially, it's like this, where you have this model, right? That's kind of the point, or sort of where it comes from. I have a webinar where I did a better job than just this ridiculous model here, right? But essentially, with an electrochemical process, it's a way to describe the charge distribution within a semi-infinite pore. And so where it comes from, to sort of address your question, is that in the 60s, there was some proposition of using a transmission line for porous electrodes, and then the one that people cite often is DeLevy. I don't know if I'm pronouncing it exactly right, but it's actually this. Here, I'll share the tab. This one. So this paper here, for example, this is from the 60s. So this is a DeLevy on porous electrodes and electrolyte solutions, capacitance. So, and I think this is the paper where he proposed the use of a transistor. This is I don't have the access to the whole paper. Of course, this is just the abstract, but essentially this is where I think one of the first instances where the transmission line was like introduced to do this for electrochemical processes. And then the last bit is that the electrochemical concept has been probably most clarified, at least in my estimation, from the work of Juan Bisquer in about 25 years ago, in the early 2000s. He has put a lot of work, papers, doing a lot of extra clarification of this, the transmission line model for porous electrodes. And then as far as the termination, so like the application of the transmission line electrochemically, and this might maybe answer your question because I don't know enough about the theory with the electrical, like, which is where it basically comes from, right? But this is basically your transmission line, right? So one of these is the ground, one of these is through the wires, and one of these is through the poles. And so when you model it on a, electrode pore, one of these sides is through the electrode, one of these is the electrolyte, and one of these is the interface between electrode and electrolyte. And you have edge effects. And so basically you can have an open or a short where you have infinite or zero resistance on the ends. When you effectively solve the equation, you can you can, in our software, for example, you can change the end effects. You can change the end, what it is. Basically, you can change the interface between whatever, but it's a way to, of course, capture the distribution of charge within a pore. And so you do a semi-infinite sum, and mathematically, and then visually, this is what it usually looks like, right? Like Haifa mentioned earlier, you have sometimes this 45-degree line at the higher frequencies, and then sometimes it curls away. Sometimes you have a little semicircle after. The behavior can depend based on what the shape of the model is, but effectively, to your first point or whatever, is that it is exactly supposed to be analogous, as far as its relation to all of the electronic theory. I don't know the electronic theory all that well, to be honest. A transmission line has a characteristic impedance that is irrespective of its length based on the distance between the. I think that's where the semi-infinite sum or the infinite sum kind of comes into play. And it has to do with that distribution of charge throughout it or whatever. I think this is more about the electronics here. You say that to get full power transfer without reflection, you terminate it with the same resistance as the characteristic impedance. I see. Okay, so that end resistor, for example, you would choose to be 50 ohms or whatever you have, right? And so that's probably something in electronics you would do. And as far as the application to electrochemistry, I don't know that it goes exactly that way, right? Because you're analyzing it's a microscale versus a macro scale, and whether that's exactly analogous, right? There's a it goes from the hot size, right, the electronics model or whatever, down to microscale for electrochemical application. As far as all those specifics that you're talking about, you clearly know more about it than I do. The power transfer reflections, if it translates directly, maybe. Most of the language, for example, if you read like One-Bit-Square's papers about it, the language isn't always discussed that way. You know what I mean? It's like it's more electrochemical language than electronics transmission line language, if that makes sense. So it's like using the model to describe your electrochemical processes while talking more of it as an electrochemist than talking about the power transfer or whatever things that would make sense to an electrician, for example. So it's hard for me to answer those questions. They're good questions, to be honest. But what I will say is that there's probably more to what you're saying or writing here, as far as legitimacy to these analogs and about what relates to what, simply because a lot of electrochemists think very highly of the transmission line model compared to almost every other analog, because it is considered to be the most real, the most relative to reality, real way to describe your system. So it's really beneficial to delve into it, in my estimation, because it is one of those highly regarded, if you put a CPE, you can publish anywhere, but a lot of EIS people get very oh, you should never use a CPE. It isn't real. And then they have a point. They're not wrong. It's just, what other option do we have? Anyway, so that's a little bit of a tangent on transmission line, but yeah. Here's a question. Pratish has another question about galvanostatic. Is galvanostatic charge discharge measurement similar to it is chronopotentiometry? Yeah. At least partially. Yeah. So it is. Yeah. Chronopotentiometry, if you break it down, chrono, time, potentiometry, potential, metry, right? Measuring, changing. So you're measuring the change of potential with time by setting one current. So that's exactly what galvanostatic charge discharge is. You set a current, you're measuring the potential change with time, chronopotentiometry. Yeah. And that's exactly what it is. And so with a charge discharge, galvanostatic charge discharge, it's in galvanostatic mode, which means you're controlling the current, which necessarily means you're measuring the potential of the voltage. You set a current positive, let's say, when you're charging, the voltage changes and you go until the voltage reaches some point, let's say 100%, whatever your upper limit is, and then vice versa for the discharge. So yes, they are one and the same.
Yep. Let's see. We have a question. New question just came in from Zoom Zunaria. Zunaria.
Zunaira.
Zunaira. Sorry.
Yeah, we did say that we would get names wrong. So.
Yeah. and it's funny because there's another person who has like a very similar like animal, like a cat.
Yeah.
Like Bahar also has a cat. So I'm like, oh, is this the same person? No, Bahar
Slightly
has
different.
a cat. This one's a different cat. How can we measure conductivity from impedance data without using any software? Oh, that's a really, really good question. So I'll tell you just a little bit of. I had a similar issue with somebody actually at Case Western Reserve. One thing to keep in mind is that conductivity is very much looked at as like a static value. Like, what's the conductivity of the system? That's the same as kind of saying, what's the resistance? It's the inverse of saying, what's the resistance of the system? And impedance is more, gives you more detail because it's a frequency based experiment. You're looking at the impedance as the resistance as a function of frequency. So when you take EIS data or impedance data and you want to get a conductivity, you are going to get the conductivity as a function of frequency. So you're going to get a lot more information than just conductivity, something to keep in mind. But that being said, I mean, I don't know if you know if that like anything, but it's like you're going to like impedance has a real and a complex component to it. Most of the time people just do 1 over the impedance is the conductivity. I don't know if it's as simple as that. Maybe 1 over the magnitude of the impedance will get you a quote conductivity measurement.
So there's actually Chris made a good point. Essentially what you just said there, which is, yeah, you can use the reciprocal of the impedance, but there's a bit of nuance. Yeah. I mean, so I guess the point is if you don't have any software, I assume you have some data, some plot. So if you have a Nyquist plot, the quickest and dirtiest and easiest, whether it's accurate or not is another question, but way to get it is if you're able to have a Nyquist plot and you have some points at high frequency, well, you don't have to go any further. Basically, you can just assume whatever the Z real is of your impedance data, where the ZI is closest to 0, that ZR is some resistance, some value, some amount of ohms. You can just do 1 over that Z real. So that's what Chris was saying with some nuance. Yeah, okay, whatever. But that's a very quick and rough estimate. So 1 over ohms, right, is Siemens, I think, right? And sometimes you need to do, that's supposed to be an ohm, by the way. Sometimes it'll be ohm centimeters or whatever. So actually there's another expression, right? It's what L over RA is equal to sigma. Sigma is sometimes used for conductivity. So this will depend on the exact system you're using. Yeah. So this, I know it's like, what is L and what's A? Well, A is surface area and L is like distance, length, characteristic
like
length, distance. Sometimes people, if they have like a cylinder, this is where it gets tricky. And this is a hard thing. This is like, talk about engineering and stuff that doesn't have any real answer or whatever. It's like you have a cylinder, they might use like the surface area of the outside part here, and the L might be the diameter or the radius or something. You might use that. If you have like a spherical particle, maybe L is the radius and A is the spherical surface. Like it's nebulous exactly what this is, but sometimes these dimensions are thrown in there. And so you end up with, this is in like Siemens. Is it Siemens centimeters or Siemens per centimeter? It's L over R. So that'd be Siemens per centimeter, I think so. Because this is like meters. This is meters squared. And that's Siemens per, so Siemens per centimeter, because the reciprocal is ohm centimeters. I always get mixed up with this thing too. It's always odd to me, the length unit within Nyquist plot data. Anyway, that's a separate issue. The point is that whether or not you have a length unit in there or not, it's basically like the reciprocal of the impedance at the highest frequency, essentially, where either your minus ZI is closest to 0 or on your Bode plot, your phase angle is closest to 0. Either
Mm.
one is roughly acceptable. And at that case, you could use if you just have a Bode plot, let's say, for example, you can use the Z magnitude so like something like this, you could use the Z
Yeah.
magnitude where the phase angle is closest to 0, and then take the 1 over. And that's also a rough and dirty estimate of your conductivity. And so that doesn't
Yeah.
involve anything as long as you have the data, I guess.
Yeah.
That's it's not a perfect way to do it. As Chris said, there's some nuance for sure, but it is a perhaps feasible way to get a quick estimate of what the conductivity is
Yeah.
with
Yeah.
impedance data. Let's see.
I mean,
There's a few other questions that are rolling in now.
Yeah.
So let's see. What is the main purpose of doing CV to study charging and discharging behavior of material? Yeah, not a lot, to be honest.
Yeah.
Sometimes people will do CV on like battery electrodes as a way to make sure they are going to work almost, but you do CV really, really slowly. It's almost like a different way to charge and discharge, because you still will see like peaks or whatever. And sometimes you do that, like, okay, so like for example, lithium sulfur batteries have like 5 billion oxidation states. It's like LiS1, LiS2, Li2S5, Li17S43. It's crazy. Lithium sulfur has like a million states. So like maybe you do CV on something like that and you get a
Yeah.
bunch of peaks for each oxidation state or something. So
Oh,
you're trying to
interesting.
see like if it's working and if they're all there. Like, why else do you do CV in any system, right? Whether
Yeah.
it's battery, charge, discharge, or anything. You're trying to see if you have a redox reaction, right? A peak somewhere, and try to find its position or whatever, see
Yeah.
what voltage it's happening at or something like that, right? So
Mhm.
similar phenomenon. It's just that with charge discharge stuff and batteries or whatever, most of the time you're going to use a galvanic static process to drive that reaction, preferentially, I guess I would say. So to some extent, I guess the answer is the same reason everybody else does CV, which is to find the processes and the reactions, the potentials at which they happen, and especially for complex stuff where there's a lot of, I don't know, oxidation or redox states,
Mhm.
right, that are present.
Interesting.
Okay,
Interesting. All right.
what's
So
next?
looks like we have Jagannath, I hope. What is the necessity of using 3 electrode system instead of 2 electrode system? My favorite subject. So Jagannath, let me share my screen. Hopefully it's showing up. It's funny because we're going to use almost the same kind of system. I'm just kind of decrease it. So the way I like to think about the difference between 2 and 3 electrode systems is, and let's just say we have some solution in here, is you can have a 2 electrode system. I can have one electrode here. I can have another electrode here. Let's see, just make sure this is showing up. Yep. So I have my 2 electrodes, and they're connected to some power supply, some kind of voltage. Let's just do the V. And I can drive reactions to happen at one electrode and drive other reactions at the other electrode. So I can do electrochemistry in the 2 electrode system, right? I apply 1 volt or 2 volts or something, and I can get stuff to happen on one electrode and another. But the question about what is the kind of absolute potential that these reactions are occurring is kind of unknown. So one of the reasons that we implement these 3 electrode systems is because we're trying to answer the question of like, what is the voltage? Like, what is the potential of the reaction? So we're looking for what's the potential. That's why we implement a 3 electrode system, because even though there's a voltage difference between these 2 electrodes, it's not a stable point. If I'm really interested in learning what's happening on this electrode, well, the potential of this one is changing. So even though I may have, let's say, a constant 5 volt difference between the two, I don't know if it's like, well, maybe this is -3 and +2, or +3 and -2, or I don't know what that is. So what's commonly employed is actually a 3 electrode. And in that case, what we do is you can kind of conceptually think of this as a voltmeter. So this is actually like a measurement device. There's a little dial, so that's what measures it. And then we have what's known as a reference electrode for a 3 electrode system or 3 electrode setup. And the potential of this reference electrode is not governed by the electrochemical system. It's not governed by any of these other things. It's not changing. So I can measure the voltage difference. I can measure this, right? This comes up on a screen, right? It might be 1, it might be 2, it might be something. But I know that the potential of this reference electrode is not changing. It's stable and shouldn't be changing, which means I can attribute any potential changes to this electrode, what we call the working electrode. So that's the main reason why we employ a 3 electrode system, is we want to have a stable reference point while we're doing electrochemistry experiments. And a 2 electrode system inherently changes the quote stable reference point. And additionally, even though I have like a voltmeter and a power supply in this picture, you really need a potentiostat to do a 3 electrode experiment, because you need feedback. If you're telling the potentiostat, hey, apply 1 volt between the working and reference, you need feedback, as this is what's known as called the counter electrode or the auxiliary electrode. You need some feedback to make sure that that potential is being maintained. That's a potentiostatic experiment. So hopefully that answers the question of the difference and why you would want a 3 versus 2 electrode system. Okay.
Now all of a sudden the floodgates are on, right?
Oh yeah. That's fine.
It's
It
good.
happens.
Yeah, we've had
It's a little
a
slower
lot here.
earlier.
I'll try to get to. I see Zanera. You've asked a bunch of questions. I'll try to get to those in just a minute here. But Pratish, I think last question. I assume this is still sort of with reference to the galvanostatic charge discharge discussion. So I'm assuming you're sort of referring to some battery experiments, things of that nature. What should be the parameters range we should give while measuring chronopotentiometry with some example? I'll try to give a brief example here. It's a bit of a complex thing, especially if you're talking about the battery charge discharge process and things like C rate. But very briefly, when you're talking about a charge discharge process, you're talking about the time and you're talking about potential, right? And so if I set some current, I is equal to whatever, some current, 1 milliamp, then I have my potential will increase over time. And if I set it to -1 milliamp, my potential will decrease over time. The parameter and the rate at which you apply and the voltages around which you measure depend entirely on the system you're studying and the battery that you're studying or something like that. So like as one example, like a lithium ion battery, it's my favorite one. It's what I studied in school. It's one I know very well. So a lithium ion battery, lithium ion. A lithium ion battery usually has a voltage range between 3 and 4.2, depends on the exact one. Volts, okay? So this might be 3 volts, this might be 4.2. So there's your range with your parameters exactly for the voltages you're going to measure between. So like you're going to set a current until you hit 4.2 volts and you're going to turn off the current. You're done. You're going to set the current negative whatever until you get down to 3, and then you're going to stop applying current. You're done. You've discharged entirely. As far as what current you apply, that depends entirely on exactly how big your battery is, because that's what its capacity is. So if your battery has 1,000 milliamp hours of capacity, then if you apply 1,000 milliamps it will take 1 hour to get from 3 to 4.2, or other way around, assuming you start. Let's say, so if you have a 1000 milliamp hour battery and it's at 3 volts, if you apply 1000 milliamps in 1 hour, it will be at 4.2 volts, and then vice versa. If it's at 4.2 and you apply minus 1000 milliamps, after 1 hour, it will be at 3 volts. If you have a 1000 milliamp hour battery and you apply 2000 milliamps and it starts at 3 volts, it will get to 4.2 volts in, anybody, class, how long? 30 minutes.
Yeah, half an hour.
Half an hour, exactly. So this is just one example with real numbers for you. You're applying your current twice as fast as its capacity, rated standardized for an hour, so it will last half an hour. So there you go. That's and how these capacities work and calculating them is a longer discussion. I'm sort of curtailing that for now. I can talk about it more if there are substantial interest. I can show you where that comes from. There's a handful of questions from Zenara I want to get to, or we can both get to here. But that's some examples of like numbers for charge discharge processes and where they come from, I guess. Why sometimes the real part of the impedance is negative. So yeah, Chris actually chimed in on this as well with a good answer. Essentially, he's right, is that the negative real impedance is either a pure artifact or possibly a secondary reaction taking place skewing the reference. Yeah, so if it is something, so I'll just share again and draw another thing for you. So negative real impedance is almost certainly garbage. Just that's the short answer.
It's an artifact.
Yeah, it's almost certainly garbage artifact. You should ignore it. But if you have a Nyquist plot, right, Z real minus Z imaginary, and this is 0. If you have something like this, right, let's just say you have something like that. You have semicircle right here, you have a Warburg thing here, and you have this little tail. All of this data, trash. Get rid of it. It's not there. You're going to cross it out like it doesn't exist.
It's like heavily crossed out.
That was a bit aggressive. So, but mostly that just, it's an artifact. Okay. So in all seriousness, I've talked about this phenomenon before. I'll describe it very briefly. I know it's a bit complex. That usually comes from the reference electrode. And it comes from the fact that there is like parasitic capacitance within a reference electrode that distorts the potentiostat's ability to measure at high frequency. Okay. So a reference electrode usually is consistent of a glass tube. Let's say you have your contained like silver wire with silver chloride. This is your Ag wire with AgCl on it, right? Okay, let's just say that's what that is. Could be calomel, could be anything, whatever. You have your reference couple inside, and you have KCl electrolyte inside this glass tube, and you have a frit at the bottom. This frit right here has some amount of impedance. Let's just say this is high, but let's just say it's 10 kilo ohms. All right, so but it's a resistance. It's not going to change. There's a resistance between this internal fill solution of, potassium chloride and my bulk solution of whatever, sulfuric acid. I know this isn't exactly the reference electrode you use, just bear with me here, right? Whatever your electrolyte is in your main solution and you have your electrolyte inside, there's some resistance there. At high frequency, the potentiostat is going to try to sense, actually really at any frequency, especially at DC tests, the potentiostat is going to try to sense the potential of this reference. Like this is connected to your reference line of your potentiostat right here, right? This is your reference electrode potentiostat line. It's going to sense all the way through this line and through this here. It's going to sense through that. So there's this impedance associated with that. However, there's another way to get from the inside where this AgCl wire is to the outside solution that is directly through the glass, which is not ideal. But there's technically a capacitor that you can draw between this glassware because there's ions on this side, there's ions on this side, and the glass is a dielectric. It's a capacitor that is about 8 picofarads, something in that range, 5 picofarads, 10 picofarads. It's very, very small, but at high frequency, a capacitor has a very low impedance. And at the very highest frequencies that you might do an impedance experiment at, a megahertz, sometimes 100 kilohertz, if this impedance is below this impedance of the frit, the potentiostat is going to try to measure through the glass. In short, that's basically what is happening a lot of the time when you have this negative Z real tail. And actually, this is another one of your questions. Let me. So to this other question here, how can we determine the real axis intercept when there's an incomplete semicircle? So two things. The first is that when you have this negative whatever kind of tail, you have two options. One, start at a lower frequency. Two, just take this point as your intercept and ignore this data because it's artifact. It isn't always the case that this point here, for example, is the most accurate like IR compensation point or whatever, the intercept, but it's a good estimate because sometimes like if you can use a shunt, there's other ways to get around it, for example. But effectively, just back to the main point here is that your potentiostat is trying to measure at those frequencies the potential through the actual glass of your reference electrode. And there's obviously no diffusion that can happen through glass. It's a firm barrier, right? So it can't, so the data is basically garbage. It's meaningless. This little tail is just an artifact. Artifact is just a way to say like it's just a weird, I don't know, manifestation of data that doesn't mean anything, something like that. So that's my best very quick description of that process that I'll give you here. I've talked about that a few episodes on this this live stream. We've talked about this a few times, and I'm happy to kind of relive that. But that's the somewhat short explanation of that phenomenon. Is there another question? I think that there's a few. I know I'm sort of answering all of them, but they're all impedance related here.
Yeah, a lot of them are impedance related.
So yeah, the last couple of questions actually look more general to me. So Zanara asks, how can we describe electronic components in a circuit to describe the material's impedance behavior? And then the other question was, what does it mean if there's series or parallel, something like that? Yeah. What does it mean if there's parallel or series combinations of resistance, capacitance, Warburg? How does it describe? So yeah, those two questions are like far too general, let's just say, to answer succinctly. I, for example, have on our YouTube channel, you can find in the webinars section, if you are a member of you can join to be a member of our YouTube channel. Shameless plug. Webinars I've done like a whole 5-part impedance webinar series where I talk about all of those things, like different, what processes are represented by which resistors, capacitors, Warburgs, what electrochemical processes are happening, and what properties you can measure using all these different circuit fit and analogs. If you're asking what does everything mean, it's like that is a very loaded question, right? I can't exactly answer that easily and very quickly. The shortest answer I could probably give is that resistance usually refers to some charge transfer process, which is a Faradaic process. Capacitance refers to usually a non-Faradaic or parasitic process. At the most bare bones general answer I could give is that. But really, those are questions that require a tremendous amount of time which I tried to do in my webinar, for example. So I encourage you to look at some of those if you want to, think through some of the complex ways that we apply circuit fits to those phenomena.
Yeah. Yeah. I mean, I think you described most of it pretty well, because there are a lot of combinations of circuit elements, and those combinations can mean different things depending on how you put them. I think I agree. I think looking, because I mean, Neil's webinars are like, and like this subject is like an hour long discussion, like lecture, but maybe uh, in short, when you're thinking about parallel versus series combinations, you're just looking at like, can the process go one direction or another direction, or does it like does the electron can an electron either undergo a Faradaic process, or at that same interface go through a similar parallel process, and that helps you determine whether it's series or parallel. But you have to think about it. It's not always a straightforward process.
Yeah.
Let's see. I Aziz asked a question about whether we have actually worked with sensing cortisol hormone levels from sweat. I mentioned in the chat that we haven't, but he then said that yes, it can be measured from saliva, and now they're working on a wearable device that measures cortisol electrochemically, and a University of Calgary researcher has done it. So while we haven't done it, we can talk about it, but please let us know
Some kind
specifically.
of Faradaic biosensor, back to
Yeah,
bringing things back from the beginning. We talked about
a little bit.
Faradaic and non-Faradaic biosensors like an hour ago.
Yeah,
But I assume it's something like that, right? It probably sits on your arm, and sweat is an electrolyte.
yep. Yeah,
Right?
sweat's an
Sweat's
electrolyte.
just salt water, essentially. So if there's enough like liquid salt water interface,
Yeah.
you could do electrochemistry on it, I suppose.
Yeah, I mean, we would need to. So let us know exactly what your question is about it. But in principle, our somewhat limited understanding is if there is cortisol in your sweat as you sweat, and if you're stressed while you're sweating, it'll show up in your sweat, or maybe in your saliva. But yeah, you need some kind of sensor, something that's electrochemically active. So I don't actually know about cortisol in terms of, can you do an electrochemistry experiment on cortisol?
Yeah, I guess
itself,
it must like be able to be oxidized by something
or reduced,
or
or
reduced.
something
Yeah,
like that.
exactly. I don't know also about cortisol electrochemically,
Yeah,
but I mean, it's some organic compound, I suppose, right?
yeah,
So perhaps it can be oxidized by, pick a
Mhm.
electrocatalyst, right?
Yeah, yeah.
Oxidize it. Yeah, I mean, that sounds, probably something like, for example, how they measure, like we have a lab on this with our our company, right? But it's like measuring lead in water, like
Yeah.
trying to measure contaminants, for example. So it's like lead is really, really low concentrations, but you try to measure it and see if it's safe to drink, that kind of thing, right? And so you can do like a pulse technique it basically
Yeah.
enhances the signal. You can clarify.
Anodic stripping.
Yeah. Oh, yeah. I'm sorry. Yeah.
That one uses anodic
Anodic
stripping.
stripping. Yeah. Yeah. I'm
But,
off on it. Yeah. So you plate something on and you strip it off.
Yeah.
And it's like you correlate how much you plated on, how much you stripped off. There's the current it's like Faraday's law, basically. It's like the current correlates with how much material is there and whatever, right? So something like that. And so maybe you can do a similar thing with cortisol, perhaps. Like you're doing electrochemistry and you're correlating the amount of current you get with how much cortisol is there.
Yeah.
Something like that. You make a calibration curve.
Yeah. There are I know other labs who've done, because if you're looking at cortisol and hormones, I mean, people have done a lot of neurochemicals with so there's fast scan cyclic voltammetry, neuroelectrochemistry, where dopamine has been the most studied thing. And actually they use bare carbon, I think it's either micro or nano electrodes to measure dopamine. Yeah, these little carbon fiber electrodes to measure dopamine. So I feel like you should be able to, I mean, I don't know enough about cortisol and if it's electroactive by itself. But let's see. Aziz has given us a little bit more information. I'm an electronics undergrad student. I'm interested in biomedical projects. Some proteins or antigens are mixed with sweat that react with cortisol, and there is impedance. There is
Oh, so it's
impedance
an
change.
impedance diagnostic. That's kind of cool.
That is cool,
Yeah, I guess
but that's also the thing. And we, as you just said, we literally talked about this at the beginning of the podcast. The second question was about Faradaic versus a non-Faradaic
yeah.
bio
And then to your point about
biosensor.
empiricism, I mean, this could be
Yeah.
something that's an empirical thing. So if the impedance changes,
It doesn't mean it's a
Just-
Faradaic.
it doesn't. Well,
Sensor.
exactly, which actually is useful in some sense
Mm-hmm.
because you don't. If the only change in the impedance is the result of, for example, some protein or antigen that reacts with cortisol, and there's a easy sort of a binary situation here. It's like
Mhm.
I don't have cortisol, so there's no reaction there, and impedance is whatever. And then I do have cortisol, and it changes, and you can correlate that. It's sort of like a if-then statement, something like that, right? Then it's great because you can correlate that empirical data with the amount of cortisol you got because it changes the impedance by 10%. So you have this much cortisol, like whatever.
Yeah.
So that kind of empirical relationship is really quite useful for things like sensors because you're using it in a specific application with a specific amount of controlled chemicals or samples. In this case, it's like your arm as it sweats or whatever.
Yeah.
Assuming things remain relatively like static for the same person, or whatever, all the variables relatively constant, which is hard in biological samples, of course.
Yeah.
Biomedical stuff is notoriously quite complex, especially because human beings are complex and physiologically there's a lot of stuff going on. But that being said, if you can isolate most of the variables, I shouldn't say isolate. If you can set most of the variables to be roughly the same, those kinds of empirical relationships, actually, whether Faradaic or non-Faradaic, because you're doing impedance, you might be able to have some success there. I think that's a cool idea.
It sounds like if you're an electronics undergraduate student, if you're electronics, I'm assuming it's more like electrical engineering. So you're trying to develop a device.
Yeah,
is my guess. I've talked to some people who do like electrical engineering projects, like senior level engineering projects, and it's usually done in like a team where like one person does like the electrical engineering and the other persons are trying to do the chemistry. There's a whole lot of chemistry, biochemistry involved in this because probably some of your biggest challenges are actually getting the proteins and antigens to stick to an electrode surface and not move. And that when you add cortisol and non-cortisol mixtures, you do see it. I think you will see a change, but getting a consistent change is hard. It's a good project. It's a very good project. I think it's probably a very challenging project too. But I mean, we have a few more minutes left. So if you have any other more specific questions, let us know. Scenario has a couple questions. I think we can rapid fire some of them because we are running low on time. But mostly the questions have to do with doing cyclic voltammetry for a solid material and then doing cyclic voltammetry for a liquid phase versus solid phase. So I don't have enough experience with doing cyclic voltammetry for solid materials, but I know that a lot of people do cyclic voltammetry for solids, and the nature of the response is different, but they still in many ways tell you a lot of the same stuff. You're looking at electron transfer. You're probably not going to get, like, for a liquid phase system where you have a liquid solid interface, you're getting you're getting electron transfer associated with diffusion control of a redox active molecule. Your CVs are going to look like these ducts, basically, these big ducts. With solid state, the electron transfer is not diffusion controlled because you have just two solids probably touching each other. So your voltammograms are going to look a little bit different. They're going to be a little bit more instantaneous.
It's faster kinetics, right?
So, well, the kinetics may be the same. The mass transport's a heck of a lot faster.
That's what I meant.
So that's kind of the That's kind of my thought. I would need to do. I mean, I have to know a little bit more about the system to know more about to speak more about solid state. But
My guess is that
yeah,
you can do cyclic voltammetry a lot faster.
on a solid.
Yes.
Yeah.
Because when you have mass transport slowing things down, sometimes you have to go slower, for example. But it's, for example, one of the reasons why solid state people do impedance at really, really fast frequencies.
Yeah.
You have the luxury of going
Right.
a lot faster because you're not limited by mass transport.
Yeah. Yeah.
You know, and mass transport is terrible because of liquid,
Yeah.
right? Liquid diffusion and whatever is, even in very concentrated salt solution, just takes a while and it slows
Mhm.
everything down. So with solid state, you're not limited by that. So my guess is that you can get away with faster sweep
Yeah.
rates and things like that. But yeah, I do think that the voltammograms probably display slightly differently. And I actually
Yeah.
don't have a lot of experience as well with solid state systems. I know some people are doing like different devices that are like polymeric, which is, I guess it's solid state.
Yeah.
Sometimes you
Yeah, it
soak
can
it in an electrolyte, which it seems mostly solid, but it's still a liquid. Even if it's a very thin level, layer of liquid, there's still
Yeah.
liquid, like fuel cells and batteries are still liquid phase because you're soaking the membrane in
Yeah.
acid or salt or something, so it's still liquid phase.
So then, kind of to Scenario's last question, could you give information about people who do it? Does that mean that, like, the recommendation is go on Google and look up solid oxide electrochemistry or solid state electrochemistry, and
Yeah.
you'll find review papers. I think batteries are good, but it's still not like complete solid state. Because you can have
Yeah, it depends.
a
Like
little bit of electrolyte.
there are some
in it.
people working on like with the separator that's like a polymer, like some solid polymer.
Yeah.
I guess that probably something that like approaches a solid state system.
Yeah.
And I'm not exactly sure how it behaves, to be perfectly honest.
Yeah.
So yeah.
Of course, has a good point. Yes, if you're looking at solid state diffusion, then your diffusion is going to be very, very slow.
Yeah,
If it's solid state diffusion through a polymer or something like that.
Of course, yeah, it's gonna move.
That's true. Let's see.
So I think that's mostly
I think that's mostly it. I'm looking at one of Chris's last questions. Do proteins and antigens change conformation in a way that changes their apparent charge? It could be. I mean, proteins, I don't know enough about antigens, but I think proteins are humongous by comparison to normal molecules. I don't know enough about changes, like when you do any electrochemical changes, if that changes its conformation. It changes its conformation in different ways. So I don't know enough about that kind of stuff.
solid state electrolytes for batteries.
Solid state electrolytes for batteries.
We nailed
Okay.
it. We got the application.
Yeah, we got the application. Alas.
yeah, that's it's an interesting thing. Again, it allows you to probe like higher frequencies and things like that.
Yeah.
And I think that some of the downsides to the diffusional liquid phase kinds of issues people are trying to, that's one of the reasons people are looking at these solid state electrolytes. But I don't know to what extent they've been successful yet.
Yeah.
I would say, I mean, from an academic and a research perspective, I think it's a interesting field. I don't know. Part of the reason you might not find much data on it, to be honest, is that it might not be something that has been heavily successful, I suppose, which doesn't mean that it's not possible. You know what I mean?
Yeah.
That some of these kinds of studies or whatever aren't possible, but just that it isn't a field that a lot of people are looking at, or that people haven't found tremendous success yet and published their data. So perhaps you could be the first.
Yeah,
I don't know.
Right.
That could be part of it, to be honest. So
you may also find that and Neil, you may comment more on it. What I have observed is that, like, there may be some people who are just doing like almost synthetic chemistry making a solid state electrolyte,
Yeah, but not a lot of testing.
and
about
not a
it.
lot of testing on it in a battery. Like,
Yeah, there does tend to be this kind of odd, like, bifurcation sometimes between people who are doing materials
yeah,
stuff and people doing practical stuff, and they're not always overlapping. Like, it isn't a guarantee that someone who's developing materials is doing maybe not any. Like, a lot of times if you develop some material, you do some test with it, like
yeah,
in whatever system it's designed for,
yeah,
but not to the same extent that someone who's studying battery performance or whatever, right, is doing. Like, you're just developing a bunch of materials
yeah,
and doing a lot of physical characterization on it, which is all good
Mhm.
stuff, right? But
Yeah.
it's like the the thorough analysis of different materials and different morphologies or whatever on its performance about some of these things is not always present, which is more to Zanara's point, could be as well why there isn't a lot of data or publications on something of that nature, because there hasn't been enough people who really published on that yet, or
Yeah.
have made a lot of those connections.
It
Something
may
like that.
also be that, like, you may type in like solid state electrolytes for batteries, but you may find that, like, they're polymer chemists, and there definitely are polymers that are electroactive. You may find it in a different, like, you just may find it labeled differently just
Yeah.
because it comes from a synthetic chemistry group that are making polymers. That's all they do. They make polymers all day.
I also feel like at every conference,
Mhm.
there's like, there'll be like battery symposia or like a
Yeah.
battery session.
Absolutely.
And it's like there's like some part of one of those, or there's some part where it's like a solid state something, but it's like a smaller degree of the battery field or something. You know what I mean? It's like
Oh yeah.
it's like it's like a subset of the people who are doing battery stuff are doing some of these solid state, systems. So it's like in and of a niche field, it's a niche topic.
Yeah.
So it is not surprising in some sense to find not a ton of data on a specific kind of subset that you're looking at, because I think that it is actually quite I don't want to say understudied, because it really depends on what its actual promise is, which I don't know
Yeah.
enough exactly well to comment. For example, all I know, for example, is that most commercial batteries in consumer electronics and whatnot um, are using not solid state stuff, right? Which doesn't mean that it's never going to work. It's just that right now it's not the state of the art, right? So I don't know how to accurately assess whether it has real promise for the future of replacing some of the state of the art technology or not. Perhaps it does, and it's just like anything else. It just needs more attention and research. Yeah, of course, that's certainly the case. Yeah. What do I think of quantum batteries?
Yeah, he's asking. I've never heard of a quantum battery before.
I was gonna make like a really bad physics joke.
like
something like, well, I thought about it, but I couldn't remember where I put it.
Yeah, or like
there was a 50% chance.
It was a 50%.
There's a 50% chance that I have an answer for you, but there's a 50% chance that I don't, and they're both existing at the same time. I don't know.
Yeah.
Some like really stupid Schrodinger answer.
Yeah, quantum.
I don't know. Honestly, I assume it just means a really small battery. I mean, what else would it mean?
Yeah, I'm trying to figure out like what is it?
Is it a real? I assume it's a really small battery, right? Quantum is like really small.
Well, but I feel like,
or is it something completely different?
Or it's based on quantum effects, like the science behind it. Unlike key takeaways: quantum batteries have the potential. Yeah, they have a lot of great ideas. Unlike electrochemical batteries that store ions and electrons, a quantum battery stores the energy from photons, which is light. Quantum batteries charge faster as their size increases thanks to quantum effects such as entanglement and superabsorption. They will not be able to power electric vehicles, but could improve the efficiency of solar cells and be used for small electronic devices. Ultimately, the challenge is to evolve these batteries, as these devices could serve as a true small off-grid power sources. I need to learn more about it. I've
Well, the
never
real
heard of
answer is
these.
that that's all made up. Next question.
It's not electrochemistry according to this. It's quantum mechanics.
It's quantum mechanics eludes
This
me.
is asking anything about electrochemistry.
Yeah. That's a cool idea.
Yeah.
But yeah, I don't know very much about quantum physics, and every time I hear something about quantum entanglement, I just assume it's made up. It's like there are certain, you know how, I don't know if, did you have this, like there's certain things in the world of science, whether it's other fields like astronomy, I would say astronomy, like space travel and like
Mhm.
physics and stuff like that, where it's like I I just don't know that I don't understand it at all, and I would just rather believe it's made up and not real and just move on
Mhm.
with my life. Like I just like quantum entanglement and all this kind of stuff. Like I don't what like what is this is crazy. It's crazy. It's not real. It's made up. It's fake. It's all fake. I don't believe it. I don't believe it's real. It's just like it's like what's the one that like I learned about it a little bit probably in high school or in college. It was like dark, like there's like dark matter and dark energy, and it's like,
Oh yeah.
to my knowledge, it's like when we do like theoretical calculations of the universe or whatever, there's like error, it doesn't work out, and so we just say like, well, the mass that we can't figure out what it is, that's dark matter. It's like that's just made up. Like really. That can't be real. I'm sorry. It just can't be real. Someone's gonna be like, "Well, actually, it is," and I'm sure you're right, but I don't care. It's not real.
That sounds like the one from the Matrix. It's just like the
Yeah.
systemic anomaly.
Yeah,
It's
it's
like a
just-
rounding error in math is the cause of
Yeah.
of dark matter or something. It's
Dark
like
matter and electrons and positrons. I don't believe in positrons. I don't believe in them. I don't know. That's a weird religion. I'm not part of that religion. Like
yeah.
there's electrons and then there's positrons. I don't know.
Yeah,
Some
we're
of
not-
these
we're
things,
not in there.
some of these things are beyond my ability to understand. I don't get it. It's all strange.
Yeah. All right. We have a question from AJ. I think we can answer this one or talk a little bit about this. But my question is, if the induction at high frequencies varies into capacitance by changing the cable connection, what could be the reason for that? I think there's a couple things we need to kind of unpack with this question. So the cable, so in the high frequency regime, we've described there's a lot of problems. There's a lot of things that can happen, but cables, just your cell cable from your potentiostat to your electrochemical cell, has capacitance. It also has inductance, and inductance is a little bit easier to understand because we have like magnetic things that are coiled around just within the cable. So there is induction. There is a little bit of induction. Now, one thing AJ is mentioning here. Let me see if I can pull up. Not coiled 4-wire mode are separated from each other. Imagine two cables working and sensing on one electrode, counter and sensing on the other.
Yeah. So it's a 4 electrode system.
So it's a 4 electrode system. So like, why is there inductance? Well, first, I think you inherently know a little bit about this is just a guess, but I think you know that you can cause certain levels of induction by having cables twisted or wrapped or looped, and even though
It's actually the opposite. It's
Or
actually more
you
that when
decrease.
you can actually remove inductance by
Twisting cables.
twisting the sense lines together and twisting the
drive
twisting the
lines.
drive line. So, for example, well, just as a general answer to your first part, it's like I'm not remotely surprised that any capacitance or inductance changes based on your connection. That's what it is. It's like your connection has to be pretty much exactly the same every time if you can, as long as you can avoid it. Or you'll get those problems. So like if you have a 4, but to your point about coiling, right?
Mhm.
Just to be clear, if you have a 4 electrode thing, if you have sorry, I wanted to use the right color, like consistent colors here. I'll label these in a second. If I have, for example, working electrode drive and counter electrode, there's a drive line. And then I have working electrode sense and reference electrode, and that's a sense. So S is sense, D is drive, just to be clear, right? You'll have to do this upstream or whatever, but basically if what you can do is at somewhere upstream is coil, you're just twisting these in, around each other, the sense lines, and you're going to separately twist the drive lines, until you get to your potentiostat or whatever. You'll have to like untwist them at some point close to your cell to, reach the points you're trying to plug. But basically that kind of looping together can actually help remove some of the inductance, for example. Not necessarily always. It depends. Like sometimes the lines are shielded and it doesn't always help or whatever. But that's one way to try to remove that and get more consistent results. You could try that. That's one suggestion.
I don't know exactly what AJ is talking about. He first says they are not twisted. They're very small, separated. Okay, got that. That's their position. But then he says, please the connection cable. And then I tell how I change connection.
Not sure what.
I'm not sure
They're
exactly.
not twisted. They are very small and separated from each other.
But like the movement of cables, just cables sensing things, and their relative positions can cause very small changes, like very small changes to things like inductance and capacitance and stuff. Small, we're talking very small. Most of the time, a cell cable has a kind of set capacitance and it doesn't really change. But if you have a different cable and it's longer or whatever, then it does change. Or if it's moved into a weird configuration, it may induce some capacitance, some inductance, some things like that. This is like a more, say, more perhaps electrical engineering type of issue. But that can happen when you're doing like a 4 electrode experiment, and it might manifest itself in the EIS. So working encounter face to face. And since the lines are also face to face. Now, the induction and the capacitance is in the cable section. It might not necessarily be at the ends, but it could also be at the ends. I don't know if we're making any progress per se, like why.
I assume you also have the sensing lines on the inside. The sensing, usually in a 4 electrode setup, the sensing lines are close to each other. The drive lines are outside.
Yeah.
So there's that. Honestly, to some extent, the sad answer here is that there's just a lot of trial and error. You're going to want to find the optimal configuration. So you have them face to face. You might choose to like the sense lines are the ones that you want to have the most intimate knowledge and control of the distance between the sense lines, whatever they're connected to. Right. That's where you're measuring your conductivity or whatever it is. It's the distance between where the sense lines are. The drive lines being a little bit farther outside or something like that is usually okay, because the drive lines, like the compliance voltage of your instrument, will make up for any extra small distance between the drive lines and everything like that. So it's the sense lines you want to have that are close. And then Chris is talking about shielding. So I mentioned about whether the cables are shielded or not. Be sure that the shield is only connected at one end of the cables to a common point. You could have some antenna or some other kinds of odd things that are going on. But ultimately, you just want to really find the configuration that gives you the most consistent results. Because fundamentally, to the main part of your question, which is that why is it changing when I change the way it's connected? It's like, I can't imagine a situation where it wouldn't change if you change the way it's connected. Like, that's always going to be the case, almost especially with impedance and especially with a 4 electrode system. I mean, it's electrochemistry is quite tricky and finicky to get consistency in general, and then you add on top of it impedance and everything. So what your goal is essentially to find what appears to be somewhat of the most optimal solution,
Yeah.
and then try to go with that. Would be sort of the most general advice that I can give on that.
Mm-hmm. All right. I think we've gone a little bit over.
Yeah,
our
we
normal
have.
2 hours.
Well, we didn't have too many questions for like an hour, and then it's
Yeah.
the last hour plus has been like a lot of questions. So yeah, thank you all for joining us. I think I don't know, somehow the different timing people join. It's one of those. It's one of those things. It is what it is here. But should we answer this last question here? I think maybe.
Yeah. If you think we can answer this last one.
Try to answer this last one pretty quickly here. What are all things to optimize when working with galvanic exchange process to develop a uniform layer material, say some platinum on reactive metal? So you want, okay.
Could be a lot. I mean, I think solution conditions are usually pretty important for uniform layer.
Platinum on some reactive, like, okay, so if you're trying to make like a platinum layer on some electrode, you are going to have parasitic effects like capacitance. So you apply some current, and you can do like Faraday's law of electrolysis to determine, like, based on however many moles of electrons per mole of thing with its density and the time, like you can get a rough estimate of how many coulombs were applied, and then how much that would correlate with some amount of thickness, but you'll have to know, take away whatever amount of the current is due to other effects like the capacitance, so there's going to be a little bit of that's one of those optimization things, is trying to pick, and if you pick a current that's too large, for example, you might start to form like a passivation layer. You might have some other kinds of stuff. You might end up with like the resulting voltage or potential is quite unstable. So one of the optimizations is picking a current, or like Chris says, a current density should be even. Pick a current or a current density where your resulting potential is roughly stable, because that potential, that is the result from your galvanic process. You're choosing some current, whatever the resulting potential is. If that's roughly stable, then it's driving, like, it's setting which processes are like thermodynamically possible. So you want to try to do something like that.
Position of the counter electrode.
Good.
Shape of the counter electrode is another thing.
Yeah, large counter electrode that will help prevent having to crazy like compliance issues with your potentiostat. The last thing I would say in general, I suppose, and maybe if you have any other suggestions, but it's like, in general, if you can plate, and maybe not everything works exactly this way, but in general, I would say if you can plate like slowly with lower currents, you'll probably get a nice, more uniform. It's like charging and discharging really slowly. It'll be more like, it'll be less prone to like pores and holes and like incomplete process. So if you can, plate like a nanoamp at a time, it's like going to take you forever, right? Like you don't want to have to sit there for 9 years to plate, a micron surface or a nanometer surface, whatever. But the slower that you can tolerate, probably the more uniform your surface might be. It's just my guess. Whereas if you go really, really fast, you might, like really high current, it might not be, you might be doing other stuff. It might not be a smooth surface. It might build unevenly, stuff like that.
Yeah.
So that's my guess. But yeah, I mean, and ultimately it's like put a film, and you're going to have to do some physical analysis, to see how level it's, you said leveling. Yeah. To see how flat it is. Afterwards you can do some SEM, or you can do some EDS to see the elemental composition. Like there's a lot of stuff you'll do afterwards to check how good your film is after you've done it and stuff like that. So hopefully that's talking through that process a little bit for you. And I think with that, we're gonna wrap this up, because we've gone over by a bit. Yeah. So,
yeah.
But
we can answer more questions next week.
Yes.
So stay tuned next week for another edition of Ask Us Anything About Electrochemistry.
And I want to plug again. I mentioned this last week, but we're a podcast is coming. Alex and I have been working on a podcast.
Yes.
and it's mildly academic and heavily ridiculous. So
Yeah, so stay
We're-
tuned for
we
that.
play, we play some games, and we tell some stories, and you know, we laugh and we cry, and we interview some people, and well, we
Yeah.
don't cry, but we do interview some people.
Yeah. Yeah. Make that
Anyway,
cry.
wherever you get your podcasts, within about a month or so, check us out, the Electrochemistry podcast.
Yeah.
It's coming.
Yeah.
So
Yeah.
there's your little plug there. So thank you, Chris. Thanks for joining us again.
Yeah.
Appreciate your help and your insight.
All right.
And,
Have a good
yeah.
one, everyone.
Take it easy.